to end with the summary. So before we start, I just like to give you the overview of our research center. Right? The name is Functional Advanced Materials Engineering. Right? So we actually conducted research, complete almost the whole loop of materials development, starting from materials synthesis and characterization, right? With the focus on bio-inspired materials, degradable polymers, right? And also we conduct work right, on computational analysis and also design right, of products that are made from the materials that we synthesize. And after that, we also develop like processing or manufacturing process right, for fabricating or making that the polymer that or materials that we develop into products. Right? And we try to get the final product into commercialization. And on the aspect part, right, we also have some work that are related to the use of plasma technology and also microwave technology in chemical recycling of materials or enhancement of properties of materials. Right? We also develop analysis, chemical analysis devices or sensor, right? Especially for chemical analysis. So this the overview right, of the work that we have conducted at our center or CEO FAME. So for today, right, I will focus on polymers that play the important role in circular economy. Right? So I think the majority of you may know already, right, what circular economy means or what circularity means, right? However, I just want to emphasize a little bit here. Right? So if we look at this picture here, this is a plot that can give the information about the quality of living of human, right, in different countries in the world. As the y-axis, which can be described as a human development index, right, starting from low number right, to 1. 1 means developed countries. Right? So the people in developed country can have very high quality of life, like can live in a good environment, something like that. However, if we look at also the y-axis here, it describes the ecological footprint, right, or how much resources, right, people in each country need to use or use in order to live their lifestyle. Right? So we can see that in countries with low value of development index, right, they also use quite low number right, of ecological footprint. Right? But with more developed country now, right, you can see the number increase higher and higher. Right? The highest one go to around 11. So the unit here is the unit of area or bio capacity per person, right, per year. And if we look at these two dashed lines, right, it represents the average value, the world average value. In 1961, right, is around 2. Right? Now, in 2007, right, it increased 2 times, right, to about 4. Right? This is the average value. And you can see that because of this, right, people need very high amount of resources. Right? They use high amount of resources in order to develop the country or living comfortably. But it is not good to the environment. Right? So if we use more resources, we also produce a lot of pollutions, or we will face depletion of resources in the near future. Right? So recommended by UNEP here. Right? So we should, right, the ideal scenario is we should go into this green area, right, within the environmental limits, right? So if we can live a very comfortable life, but using or produce only small amount of ecological footprint, like lower than 2, this can be a sustainable development for human society, right? But it is a very challenging, right? You can see some country, right, use more than 10, the value of 10, right? To get this into lower than 2 is maybe very, very challenging task. So what can be the problem of that, right? So the problem of that is, in the past, we live in the economy that we call linear economy, right? What does it mean? So we use resources, right, from the earth, and then we use the resource to produce our product, right? Production. We consume, and after that, we just throw away, right? So it becomes waste. And so from the good resources, I go to very low quality waste, and also can be hazardous or toxic. Right? So this is not good. So we can call throwaway society. And recently, we also doing better, right? We try to implement the concept of recycle, right? So instead of throwing everything as waste, right, we can take some of the post-consumer product, right, and convert them into new products, right? So we call recycling. But the recycling concept here is considered as downcycling, right? Downcycling means the properties or the value of the product that we get here is lower than the product that come from original resources, right? So this is better, but not the ideal situation, right? Because we still need to use some more resources, new resources, the black color, and also we throw away some of the waste as well, right? The ideal situation should be this one, right? We can complete the loop, right? So if we can do this, right, we call this circular economy, right? So we can take the resource that we use now, right, make them into sustainable production, right? Also sustainable consumption, right? After use, we can convert, right, the post-consumer products, right, into a new one. Right? But the new product have the quality, right, at least equal to the one that made from new resources, or even better or higher value. Right? So if we can do this, right, there is no more need, right? We do not need to get any new resources, and we do not throw away any harmful waste to the environment, right? So this is the concept of circular economy, where everyone, right, in the world, every country try to practice in order to go to this goal, right? Like close the loop, circular. And there are many approaches, right? Many steps, right, we need to do in order to go to the circular economy, right? This involves every sectors, right? In the industry, in the consumer part as well, right? This is one of the picture that can summarize, right, the overall picture, right? If we make products, right, it can be made from renewable resources, and some of them are finite materials, which means if we use them, sometime they will be used up. We don't have no more availability in the future, right? But so this can be divided into two parts, right? This part is mainly concerned with some service, some maintenance, and also recycling of the finite materials, right? So we need to concern in every aspect of this, right? On this part, for the renewable resources or the materials, right? So after we make them into products, into the service, right, we should also find a way to reuse them or to convert them back into the new raw materials or value-added product again. Right? So example of this concept that can be applied in many fields, right? So this is one example in the to apply to electronic devices, right? If we make products, right, do production of electronic devices, which is the major the industry that can cause major concern, right, in the pollution of the environment, right, the electronics industry. So it should start from eco-design, right? If we want to make product, we need to design from the beginning about the full cycle of the product that we use, right? It needs to be come with a high or long warranty period, right, in order to make to ensure that customer can use them effectively, right? Or after use, there should be a system that customer can bring them back, right? If they have some problem with the product, right? There should be repair facility or recycling facility for them, right? And everything should be designed like to complete the whole loop. Also for the biological system, right? The biological waste that we produce from our home, right, can be handled by ourselves in household treatment or to the bigger scale, right, for the community management or something like that. Now, so if we apply this concept to the plastic or polymer industry, right, so we know that plastic or polymer, right, come from raw materials, right, which is the majority of them come from fossil base, right, from crude oil, right? We convert them into building block, or we call monomers, and then synthesize them into polymer and make them into plastic products, right? So at this moment, right, we can take post-consumer products instead of throwing them away as waste, right? We can recycle them, right, or refabricate them into recycling products, right? For example, this one on the left-hand side right here, and also we can also make them into some other art piece, right, or products, right? This is also can make the increase the value of the product as well, right? So these are some practice that we have done, right? However, there are some limitations. If we apply recycling concept to polymer, right, we need to remelt them usually, and each time we remelt polymer, right, the property of the polymer will drop, right? So this can make the value of the recycling product also lower than the original product, right? So that is considered a conventional way of doing recycling, right? Sometimes we call mechanical recycling, right? But it should be even better if we can convert this polymer, right, into small molecule, right, similar to monomer, right? So into starting materials, right, that are similar to the starting material that come from the original source, right? So if we can do this, we can remake new polymer products, right, with higher value and also with better quality, right, compared to new type of polymers, right? So that concept is called chemical recycling, right, which is the main topic that I of my focus today. So in our lab, right, we apply this concept, right, into to the main theme of our research, right? So we want to develop polymers that can be degraded after use, or we call degradable polymers, right? So degradable polymers mean we can use them, right, after use. We have the way, right, to get them degraded, right, without being waste, right, or without going to landfill, right? So they can go back to the original state of starting materials. So commonly, this type of degradable polymer, right, can come from many sources. Some of them can come from petroleum-based or fossil-based, right? Some of them come from renewable resource like bio-based. And so we synthesize or develop many type of polymers like from these resources, but at the end they should be degradable, right? But another one here that fit well with the topic for today is the chemical recycling. So we apply this concept to the polymer that we, or the plastic product that we use now, and break the chain of polymer, which is very, very big molecule, right, into small molecule, starting materials, right? And the small molecule here, right, can be used to make degradable polymer. So if we can continuously applying this concept, right, into all of the non-degradable plastic now, right, in the future, we should not have any plastic waste remaining, because we convert them into degradable polymers. That is the ideal goal of this work, right? And at the same time, another the more challenging task is also doesn't matter what process we do, even in degradable polymer, when polymer degrade, they usually these usually produce CO2 into the environment, and we know that CO2 also cause serious environment, serious problem to the environment, right? So there are also active research in the field of converting carbon dioxide, right, into materials, right, or into polymer specifically for value-added products, right? So there are some promising technology now, and I think that in the near future, right, this also can be a very active research field in the future. So here, so we know that if we have plastic products and we do mechanical recycling, the property is not good, the value is lower, right? So what else we can do? So these are the slide that come from BASF. So we can convert the plastic into fuel, or we can burn them to get energy, right? But the value of that is still not so high, right? So there are some promising technology already, right? Instead of mechanical recycling of polymer, right, melt them and make them into new products, some polymer can be applied in pyrolysis process, right? Getting small molecule products, right? Gasification, or cracking, or pyrolysis with reforming, right? So this generate small molecule products, right? But the majority of them are still used as energy sources, right? So the value are not quite high enough, right? Now, what about chemical recycling? Right? Chemical recycling means breaking chain of polymers and then make them into small molecule that have active, right, functional groups, right? So if the small molecule have active functional groups, they can react with each other, right? And then forming new type of product, or especially forming new type of polymers materials with better properties, right? So these are examples of polymer in the group of polyester that have ester group, right? Ester group is considered very the most reactive functional group in polymer chain, right? We can break them, the easiest one. So in this case, if we bring PET, we can break them down in various reactions, and we can convert them into value-added products, right? It is more challenging if we apply the concept to polyolefin. Polyolefin do not have functional group in the backbone, right? Only C bond, which are very strong, right? So it is quite hard to convert them into small molecule with functional group, right? But we also have some promising technology now that we can convert them, and I will talk about this as well. So this concept is not only in laboratory or in research, right? This is widely applied in industry as well, right? So this is example of a practical approach by BASF, right? They have a division in their company they call ChemCycling that work on various type of product by chemical recycling process, right? So they can apply this into many products, right? Even tire here, which are considered cross-linked material, right? Which is hard to recycling, and they can also apply the technology to get products, right, from these materials, from these products. So in our research center, right, one of the degradable polymer that we work heavily with is polylactide or PLA. Right? This is obtained from fermentation of starch or sugar, right? And then we have a monomer, right, which is called lactic acid, and then we can polymerize this into polymer PLA, and the properties is almost comparable to fossil-based or petroleum-based polymer, right? But they can be degraded after use, right? Taking around 3 to 6 months, right, to degrade. Now, even though this is a degradable polymer, right, if we just leave it, right, to degrade to the environment, it is not so good, right? Why don't we try to bring them back and then try to apply chemical recycling to this process and get valuable product from this post-consumer product from PLA, right? So if we look at PLA, this is also polyester, right? It has ester bond, right? That is also quite weak and also easy to break, right? By various reactions. We can use hydrolysis, right? Breaking by water, by alcoholysis, right? Or we can do depolymerization, just heat them up at high temperature and apply catalyst, right? So there are various possible reactions that we can do. But in our center, we focus on the reaction with alcohol, so we call alcoholysis, right? And using microwave reactor, right? So why we need microwave reactor? This is because when we use this reactor, the reaction time can be very short, right? Only around 10 to 15 minutes, we can complete the reaction. We can break, like, very long polymer chain into very small unit, right? So we conduct research by varying different type of alcohol, right? Especially alcohol that contain more than one OH group, we call polyols, right? Starting from 2, 3, 4, 5, 6, with small size alcohol or bigger size alcohol in, like, for example, PEG, polyethylene glycol, for example. And at the same time, we also develop a prototype reactor, right, for bigger scale production, right? This is intended for community scale chemical recycling, right? So we can develop many reactor of this size and distributed this to community. So when people in the community have PLA waste, right, they can collect them and then put them in the reactor, convert this into small molecule products, and then sell this as a high value product from their process. Okay, so at the same time, we also develop process or technique that we can characterize, right, the product that come from this reaction, right? So we can make sure that we know everything about the structure, the properties of the product, and also we can vary the condition in order to get the product, right, of our desired properties or desired chemical structure, right? So the technique that we employ here is FTIR spectroscopy and also NMR spectroscopy. For example, we can use the peak at 100, 1100, right, wave number in this region to indicate the amount of ester bond, right? So if we have high intensity peak in this area, it means we have a high amount of ester. It means the polymer chain is long, right? So if this peak decrease in intensity, it means the polymer becomes shorter and shorter. So we will know the size of our products. So we can apply this to different system, right? Also, if you still remember, one of the reaction that can happen is when we heat up PLA long chain polymer, right? It also can break at the end of the chain and form a ring structure that is called lactide, right? This lactide is very important because this can be starting material that we use to make PLA again, right? So in this case, we can also develop a technique that we can quantitatively determine how much lactide is generated in the reaction. Right? So if we take mixture from the reaction, we can identify exactly how much lactide is produced, right? So, and if we vary the ratio of the alcohol per PLA from the beginning, right, we can vary the amount of lactide that can be produced, right, as the products, right, from starting from less than 1% to almost 20% of the products. And also, because this reaction can happen quite fast and also reactive, right? So we do not expect to have very homogeneous products, right? We may have a mixture of different type of product in the structure. So it is quite challenging to look at the real structure of the products, right? So we also employ NMR spectroscopy, right? Especially to the NMR spectroscopy to characterize and come up with the possible structure of the products, right? So if we know the possible structure, right, we can also determine the content, the amount of each structure, right, in the mixture of our products, right? So we also use NMR as well. So this is one example of the result that we get from the characterization technique that we develop, right? So each graph here, right, represent the yield, right, yield of each fraction of alcoholized products, right? So the blue one here, meaning that PLA is very short, only one repeat unit, right? The shortest product. The red one is bigger, right? 2 units, right? The green is longer than 2 units, right? You can see if we vary the ratio between PLA and polymer, we'll have a variation in the content of the product that we have, right? The size will be different and also the content will be different. So once we know the effect of condition, right? So effect of ratio of PLA per alcohol, like the x-axis. For different system, if we use different alcohol, we also see different results, right? So when we have the overview of this picture, right, we can decide, right? If we want to make some product, right, this specific products, right, we can come back which product is suitable for making this final products, right? We can go to specific condition of chemical recycling reaction, and we can design, right, our process. Also, we can look into the detail of chemical structure, right? So by using alcohol to break chain of PLA, right? So the alcohol will react, right, or break chain of PLA at ester bond, right? So in the reaction that we call trans-esterification, right? So if we have alcohol that contain more than one OH group, right? There are possibility that only one OH group react or 2 OH group react, right? So this gives us the product with different chemical structure, right? The product with different chemical structure also show different properties, right, and suitable for different application. So we also will have overview result, right, on different system that we can later on choose, right, specifically for specific products. So what are the applications, right, of this product that we have? Because the products now have OH group at both ends of the chain. So we call this polyols, but they are polyols that come from PLA, which is degradable, right? So when we talk about polyols, there are many applications for them. One of the common application is making polyurethane, right? If we react polyol that contain OH group at the end with compound that contain isocyanate groups, this can produce urethane functional group and join together to form a polymer that is called polyurethane polymers. Right? But the polyurethane polymer that are made from our product here, right, come from PLA. Right? PLA is degradable, so the product here is degradable polyurethanes. Right? So they can be degraded after use. The degradable properties is a unique properties of the products. However, this polyurethane also show some other interesting properties like shape memory properties. Right? So if we apply force to these polyurethanes, right? If we reheat them or we take them and wait for some time, they can return to original shape, right? So we call that shape memory. So, they also show the property that is called self-healing. If we make cut or on surface, right, or on a piece of this polyurethanes, and we heat them up a little bit around 60 degrees Celsius for around 2 hours, they can heal, right, and become a smooth sample again. Right? So this can have many applications, right? Especially in biomedical applications. Also, they show very good ductility. One of the problem of PLA is quite brittle. Right? So if we make PLA products, they can break quite easily. Right? So this is a very, very challenging problem for many researchers. Right? We want to improve the property of PLA in this way. And the polyurethane that we make here can be used as toughening agent. So we can blend this or mix this back to PLA. And this can improve the toughness of PLA. You can see original PLA can break at elongation around 4%. But if we add this polyurethane into PLA, only about 20%, it can make the elongation increase to 100, right, or 110%, right? Large improvement in the toughness. And this video that I think that can show healing behavior, right? So if we make cut on surface of this polymer and then we heat them to around 50 or 60 degrees Celsius, they can be healed, right? Right. And other applications, we can use this, right, for making 3D printing filament. And also this polyurethanes have a very good adhesive properties as well. So we can use them as glue or adhesive. So these are some other possible applications that can be applied. Another important application I want to show here is we can apply this as a template materials, right, for making nanofiber that show super hydrophobic properties. And this nano fiber with super hydrophobic properties, meaning that they hate water. Water cannot penetrate to the fiber, but they like oil very much, right? So they can absorb oil very fast, but repel water, right? So we use the product from the chemical recycling of PLA that contain a lot of OH groups, right? So this OH group can react with hydrophobic agent here that we have developed. So once we mix this together, right, we can make fiber that have super hydrophobic properties on the surface. Right? So what does it mean, super hydrophobic? If we drop water on the surface of the fiber, so the water contact angle go to higher than 150 degrees. So this is super hydrophobic, right? Compared to normal nanofiber without treating, right? So the contact angle is around 80 or 100, right? So these have very promising potential for use as oil water separation materials, right? Especially for cleaning up of oil spill, right? So, and the result here is a result on the ability, right, of oil absorption, right? So we prepare emulsion of oil in water and then pass this emulsion into the fiber, right? So the fiber can absorb oil, right, of 1,200 times, right? 1,200%, right? So 12 times of its weight, right? So the value here is 12 grams per gram of the fiber. And it can be repeated many times with almost constant performance, right, around this value. So this shows that the material has very promising property in these applications. So that is chemical recycling of PLA. What about PET, right? PET bottle that we use quite a lot here. This is not degradable polymers, right? We can also apply the similar concept, right? Breaking down this polymer into small unit, right? The smallest unit is called terephthalate, right? If we break this group of PET. So we also develop a similar process to recycling or chemical recycling of these polymers. So once we have the small molecule products from recycling of PET and recycling of PLA, we can reuse them, right, to make a new polymer, right, that combine both of them, right, both of them. So we have what we call aliphatic aromatic copolyester, right? So this polyester have very good properties of PET, right, especially barrier properties or strength, right, or modulus, but it also can be degradable because it contains PLA in the structure. Another application here is, I think, another speaker today will also talk about this, MOF. Right? Some of you may know this already. Right? Metal Organic Framework, or MOF, right? Materials that are of interest at this moment. Right? Many researchers have worked in this area. This material, right, can be generated by using metal ion and organic linker or ligand, and then with specific metal ion and specific ligand, a unique structure, right, can be formed, and this unique structure have very many aspects of interesting properties. For example, very high porosity, low density, have very reactive surface, or ability to modify the surface. Right? These are some possibility that we can play with MOF. In our lab, we develop MOF based on a linker that is called terephthalate. Right? This is terephthalate. So we can buy terephthalate and then make MU53, right, or UIO66 here, right, from this linker. However, because we also have products, right, that we degrade from PET that is similar to these materials, so we can also make MOF, right, from chemical recycling process of PET. Right? So this is fit very well with a circular economy concept. Once we have the materials, right, the material now can be used in many applications, right, because they have lots of pore inside, right? So we can use them in storage or absorption or separation, control release application. So after making these MOF materials, we reapply them into mix with PLA polymer, or apply this on the surface of other polymer or other nanofiber, right, of from other polymers, right, for different application, for many applications. So, and also this can be used in oil water filtration or oil water separation as well. Right? So I will go into detail of this in another lecture that focus on material for water purification and water treatment. Right. So these are some example of the application of the product that we can get from the chemical recycling process. Now come to last part of this talk, right? So far, if we apply the chemical recycling concept to polyester, it is not quite hard to do, right? The condition is not quite severe, and also the time, reaction time is very short, right? But if we apply this concept to inert polyolefin, right, like polyethylene, so extreme condition may be required. Right? So we also develop a process that is called oxidative degradation. So because this polyethylene do not have functional group in the molecule, no oxygen, no nitrogen in the molecule. So if we treat this with acid, right, especially nitric acid, we can break the chain of this polymer, right, into small molecule that contain functional groups. And the functional group that we observe from this reaction, right, carboxylic acid group, right, which is very important if we can make small molecule that have more than one acid group in the molecule. We can use this to make polyester, which is degradable polymer again, right? So we vary the conditions and also try to characterize or determine the nature and the structure or the content of the product that we have, right? So the product can have can be in the form of different size, starting from 3 carbon, 4 carbon, 5 carbon, 6 carbon, right? So the commonly used diacid in industry is the one with 4 carbon or succinic acid, right? So if we can make them into this compound or these chemicals, they have so many applications. And these are some results, right, on the content of each one, right? C4, C5, C6. How much, right? Depending on the time, the reaction time, right? So we can control, right, how much C4 we need, how much C6 we need. Right? At the same time, we also try to investigate the reaction mechanism, right? What is going on during the reactions, right? So more detail of this will be published in a paper shortly. So I have give the detail, right, on our work, right, that focus on chemical recycling process, right, which line up, right, or align with the concept of circular economy, right? We want to complete the loop, right, of products that are from polymers, right? We don't need to bring in new resources to make the polymer, and the polymer that we use them as products, right? When they go to the end of life state, we can bring them back and convert them to new raw material, and we can make them into new product with higher value or with better properties, right, compared to original polymers, right? So, and the example that I gave today are HDPE, which is polyolefin, and 2-polyester, PLA, and PET, right? So by using the chemical recycling process, we also develop process to characterize, right, to look at structure, to look at the content of the products, and also show some high potential application for them, right? So some of this, right, may be available, right, in commercial use in the near future. right? So with that, I also will thank the team of our research center and also granting agency who give us the support like to make this work possible, and then all of the very energetic member of our research center, right? So, and also thank you very much for your attention. Thank you.
Oh, all right. Thank you so much, Prof. Pakkorn, for your great and comprehensive lectures. I guess your how to say initial presentations is really reminding us how we develop materials as well as technology for better life quality. Yeah, you introduced to us a great concept about circular economy, how we recover resources from the waste. Yeah. Yeah, and yeah, it's amazing. You provided us many great examples how to do some processes, especially based on the chemical recycling. Thank you so much. I guess you also already conclude very comprehensively from your. I checked from the chat box. There are some questions for you, but before we move to the question and answer session, I try to continue for the second speaker.
Sure.
Yeah.
Yes. Yes.
Okay. Could you please kindly close your slide?
Sure. Yes.
Yeah.
Okay.
And okay, thank you so much, Pakkorn. And then, dear all participants, so welcome to the participant who just joined with us this afternoon. And just for your information, all of the activities in the seminar already recorded in the Zoom meeting. And for the would like to join with us through the live streaming in YouTube. Yeah, on YouTube is also already available. So you can choose which one is better for your internet connections. So secondly, I would like to invite our second invited speaker here, Dr. Witri Wahyu Lestari.
Yeah, hello.
Okay, okay, I can get your voice clearly. So,
yes, yes.
Yeah. Before you start your presentation, please give me a short time to introduce briefly our speaker, our second speaker today to all participants here. So the second speaker is Dr. Witri Wahyu Lestari from University Sebelas Maret. Actually, she's belong organic chemistry group, I guess. Yes, typically she's really intense in the supramolecular and coordinations chemistry. She graduated from Institute Witri, I guess. Because it's not English, yeah, but it's how to say Dutch. in Institute maybe food organism. I guess it's about inorganic chemistry, right? From Germany, yeah. And it's at the University of Leipzig, Germany. So very how to say delight for us to introduce this our second speaker to all of you here. And also Dr. Witri, thank you so much for your great availability to share your recent work in this seminar. And for the additional information, currently Ibu Witri also really concerned on the development or organometallics compounds and coordination compounds. And if I'm not mistaken, she already, how to say, put many efforts on some applications of this material, yeah, especially as Prof. Pakkorn also. Yeah, especially maybe Dr. Witri could share with us about the how to say the modifications of the composite system material, especially the combinations between MOF and the polymers materials, yeah, for some applications, especially in biomedicals or environmental for energy storage. And Dr. Witri, actually, in my opinion, I guess she is one of the best scientists that Indonesia have. Yeah, so far, especially the woman scientist in Indonesia. She was the L'Oreal UNESCO for Women in Science Fellow, especially in material science, on 2014. And also here I would like also to introduce to all speaker, because to all participants. See also the how to say the awardee for the OWSD Alciphaya Foundation Award for early career woman scientist in developing world in physical science. If I'm not mistaken, she been in the in the national news, because this is a really great achievement, I guess. So many great achievement that been received by Dr. Witri regarding to her excellent contribution in the material science field. So without any further ado, I guess Dr. Witri, now times and place is yours.
Yes, thank you, Dr. Khairunisa, for the invitation. It is an honor for me to speak in this forum. This is very, very prestigious forum here. Let me share my screen there. Wait. Can you see my slide here?
Oh yes, now is excellent. Yeah. Maybe you just need to how to say slide.
Is it okay now?
Yeah. Excellent, very excellent. Yes. Please.
Yeah. Good afternoon, ladies and gentlemen. Let me introduce myself. My name is Witri Wahyu Lestari. I'm from chemistry department from Sebelas Maret University. It's in Solo. Yeah, maybe if you want to visit Solo, here is my university. Usually use this picture to go abroad for the conference. That's why I put this map. And I think that the audience are from Indonesia. That's I already know, but some of the guest speaker is from some of the guest speaker are from abroad here. Professor, what is the professor from Thailand? Yeah. And here is I think Solo. Everyone is now the city of the spirit of Java. Yeah, the Solo city. If you want to visit, please welcome to our city. And what else? Yes, I am working in the division of inorganic chemistry, and my specialization is in organometallic chemistry. And after I'm back from Germany, I am working in the field of metal complexes, something like that, or metalloorganic framework and coordination polymer. And we try to innovate the synthetic method, and also the innovation, some with the polymer. We combine with polymer or with other material like zeolite or with graphene oxide or with nanomagnetic material, something like that. And we did some application in several fields. That's why I open here some collaboration with other scientists, yeah, from Indonesia itself or from abroad. And here is my small group here with my student. I have a picture here. Now, yeah, because Dr. Khairunisa asked me to speak about the polymer composite or material composite based on MOF. I will speak first about what is the polymer composite itself. As I understood that the polymer composite consists of two kinds of polymer or more. Yeah. And that's why if we want to build up a composite material, we should combine two or more material, and hopefully the important properties of the original material will still remain there, and will enhance the properties of the final or the targeted composite. And if we look detail here, that's composites material is actually close to this hybrid material or sandwich material, and it can be constituted of polymers, organic polymers, except that like what the previous speaker spoke about, and we can combine the kind of this kind of material with, for example, with metals or with alloy or with ceramic, for example, or with alumina, and also with glass, like glassy polymer also, yeah, and like with silica glass. And we also can modify with some elastomer like that. And what is the difference here, that if we have compound 1 and then compound 2, we can produce the composite material in the macroscopic phase But in hybrid material, we will have molecular or nanoscale building block. And here you can see that there are a large range of the composite material. Right? For classical composite, if you know from the material for making ship or making the plane itself, the building block is come from the classical composites. And then in the micro scale, if the composite is from there are improvement in the properties like mechanical stability and then thermal stability and photochemical stability. And in the nanoscale or nanocomposite, nanocomposite or hybrid material, we try to build up, or we can try to build up the nanocomposites from the molecule, from the molecular level like that. So the goal is how to have material with a specific combination of the purposes by combining the different molecular building block in various ratio and by controlling their mutual arrangement. That's why our challenge here is how to control the nano level of the material here. And in organic chemistry, we know that there are inorganic building block like in silica or titania. We can see here is like tetrahedral or octahedral building block. And then we can connect the building block with this moieties or with organic building block like in polymer. And here is playing a Lego, how we can connect one part to another parts and to build the functionalized material. And here what is interesting, that we can tune the mechanical or optical properties or electrical properties by choosing the appropriate inorganic building block. If we want to have good electrical properties, for example, we can choose the semiconductor, this metal, for example, or the high conductivity metal. And if we want to have like have a good cross-linking density or to have coupling side, and then we can connect with the block like this. And to have several functionality, we then can build with this organic building block. This first has been functionalized to have special properties like elasticity and has good flexibility. And here, you can see some linking the building block, some processes, as you can see, like in the polymerization or polycondensation, we can see here the polyester, for example, and then through the polycondensation, we can have like a much building block here, and then we'll release the water, for example, and then based on the processes, also we can build up the silica material based on polymer. And here, the point here that I want to speak today is about the metal organic frameworks, which can be constructed from the inorganic building block from cation or organic metal oxide cluster, which link to this at least bidentate ligand. That will form infinite frameworks, which can call as metal organic frameworks. Here is the process how the MOF5 is the first published MOF by Yaki group was formed from the tetrahydrogen oxide, which linked to this benzene dicarboxylic acid. Yes. And if we speak about MOF itself, actually MOF is a two-dimensional frameworks, but if the ligand and the metal ion itself can build one-dimensional and two-dimensional, which can call as the coordination polymer. And for two-dimensional, we can say also as a coordination network like this. The important difference or the significant difference between this three-dimensional material here, 1, 2, and 3, the three-dimensional frameworks here will have a porosity, and we can see the capacity or the nitrogen absorption capacity of this material. And by tuning the metal and the linker, and then we can apply the material according to our purpose or our targets. And as a simple mechanism here, how the MOF5 was formed. Here is the ligand, and here is the ion, the metal ion. That's the ligand itself can be changed or can be adjusted according what we want to be applied for. Yeah. And for example, for biomedical application, we can choose the biocompatible ligand and metal. And then through this self-assembly mechanism, the supramolecular material was formed. Yeah. And here is some SBU. This from in situ. SBU is secondary building unit. That can be formed in situ according what the metal that we use. For example, the tetrazinc oxide will have like octahedral connectivity here, and then the copper will have pedal wheel structure like this, and this hexa zircon tetraoxide will have a cluster that will maintain the stability of the structure. This way, the structure of this MOF is very rich and very various geometry that we can build according what we will use for. And about the principle of the MOF itself, the synthesis we can see here is isoreticular synthesis, that we can extend the linker of the MOF, and then we can see here that the basic structure of this MOF is actually the same. Just how the porosity will change according to this length of the linker. And if we use the same type of the ligand, for example, here is the linear ligand, or the ligand like the hydroxyxophthalate, and then we'll have hexagonal channel like this, and just different in this porosity or in the length. This way, this we call as isoreticular synthesis of MOF. And here, this way, we can see the structure of the MOF depend on the geometry of the metal itself, according to the electron configuration, and then the topology of the organic linker, at least the pedentate or polydentate here. And for biomedical application, we can choose several biometal ion like zinc, calcium, and then iron and magnesium, and so on. And for bioligand, we can choose like amino acid, nucleic bases, saccharide, and so on. And the important thing that the material that we have should have a low toxicology or low toxicity, and then the stability have stability during this application, and then we will have at the end we'll have a degradability after the function, after the application. And this way it will be suitable for biodegradation and properties, and will offer great promise for a bio application. Here is several MOF based on amino acid, and about application, what's the application in biomedical that I will speak is about the encapsulation of drug, and then the drug delivery system, and other application like bioimaging and biomorph drug. I will speak only at glance here. And the encapsulation of the drug actually occur based on host and gas interaction, and MOF has ability to tune the structure and porosity for better drug interaction and high loading. As you can see the picture, that if the pore of the MOF is open, and then drug can be loaded inside, and the pore of the MOF is flexible, or there are several generations in MOF. The pore of the MOF itself can be flexible, change the shape. This way in mill 523, it's called as breathing effect, and it's very good for gaspiration, but for drug loading and release also promising. And there are several strategies how to incorporate the biomedical agent into MOF. The first one is by building block approach, how we can build the linker and the metal ion, and suitable for bioimaging or for therapy, for example, yeah, and then also by non-covalent encapsulation. So the drug is encapsulated by physical interaction, and the other is by covalent encapsulation. And here is the example, yeah, how the cisplatin connected to this biphosphonated linkage and to form a like polymer like this. And it means that the cisplatin, the drug itself, is connected directly to this the format polymer, and it can act as a drug and also can act also as the media for a release itself. It's meant through the covalent encapsulation if it's like this. And what's interesting here that if we connect the cisplatin as anti-cancer drug, it has less resistant to ovarian cancer cell, and then more stable in the blood circulation because it's connected to this polymer, and then less toxicity to the healthy cell. Here, and there are several cisplatin derivatives here. What's the strategy how to decrease the toxicity of this cisplatin is by converting the oxidation state of the cisplatin 2 to cisplatin 4 by coordinating with the hydroxyl group here. So the oxidation state of platinum will increase, and then it can be encapsulated or it can be conjugated to the polymer. And in this strategy, the modification, in this modification will increase the pharmacokinetic effect of the drug. And here, how can cisplatin kill the cancer cell? I think everybody almost know, yeah, if you study the inorganic or coordination chemistry. Here is the cisplatin is hydrolyzed in water, and then the chloride group will be replaced by the water one by one, and then after that, after contacting with this cancer cell, the platinum will coordinate this DNA through this nucleus basis. This way, in this way, the cancer cell will be killed by this cisplatin drug. And the strategy here that has been employed are modification with this some hydrophobic group here in the axial position. With this way, hopefully the toxicity of the drug can be decreased. And according to Cheng et al., if the cisplatin is connected to the aspirin, and it can increase the drug targeting efficiency and cause the toxicity activity is increased. That's why if we modify with aspirin, then the apoptosis or asplatin will increase the early apoptosis, and the efficiency of the drug will be increased. That's why we just need lower doses in this case. And based on this idea, and we try to modify the cisplatin itself by isonicotinic acid in both position, because our target is how to connect this moieties to coordinate this moieties with the metal ion and to form biomorph. And other idea is we have also modified the cisplatin with the aspirin into side, and this can be a precursor for biomorph synthesis. And we synthesize the cisplatin itself by organometallic chemistry. And we start from the tetrachloroplatinum sol, and then we reacted with potassium iodide in the excess, and we will have tetraiodide platinum. And in the presence of ammonia, we will have here the two ammonia, and with two iodine here, and then after the addition of silver nitrate, we have this cisplatin. But in the presence of water, and then the water will be replaced by sodium, by potassium chloride, yeah, and to have this cisplatin, and to have the cisplatin 4, the cisplatin are oxidized with the hydrogen peroxide here. And here is the step how to make this aspirin anhydride, yeah, because after that we will the aspirin anhydride will be connected to this cisplatin and to have like the asplatin like this. Yeah. And we try to lodge the drug itself in MOF, yeah, in mil 101 iron, yeah, and the MOF itself was synthesized through the sulfur thermal methods, yeah. And we will see here the MOF has a loading capacity of this cisplatin, because this modified cisplatin is quite big molecule, and the loading capacity is around 94%. And here we can see that very slow release of cisplatin, and this one is very important, very slow release of cisplatin derivative, because the drug itself is very toxic. That's why we have to suppress or to release the drug is very slow, instead of without matrix like this is quite fast, yeah, fast in this context. I mean, and what's the problem here? That our material is or the drug itself is very low dispersion in this case. That's why we try to track the size of the drug, yeah, that we have synthesized, and still in the range of around 500 nanometer. Yeah, it's quite big. This is the challenge, how to make the drug is smaller in the nano size. And here I will tell about the other MOF that we have synthesized. Yeah, what is the we can call as a zinc BTC. This is steps from 135 benzene dicarboxylic acid, and we modify the method of the synthesis, and we study about this slow release application for ibuprofen. Yeah. That's when the novelty of this study is how to build the new method for nanomorph synthesis. And according to our study, that the sonic chemical methods has efficient result here. That after 60 minutes or after 1 hour, we have like a nano size MOF here, and we can use it for ibuprofen loading, and we study for ibuprofen release. Yeah. And here you can see that by using this matrix, there are ibuprofen release from electrosynthesized one, yeah, and also the release from sonochemical one decrease around many this one around become 25.4%. Yeah, if we compare to the unloaded ibuprofen, it's around 85.9%. This the drug. It means they have explosive release here if you compare. This way, this material are promising for a drug matrix here for drug release. And what is the weakness of the MOF itself for biomedical application? Because biomedical application needs water for medium, yeah, in the body or in the system. That's why some of MOF are not stable in water. What is the effort is how to make composite of MOF with another material. In our case, we try to modify the material based on magnesium benzene dicarboxylic acid with graphene oxide and with iron nanoparticle. And we try to use this as a metric for slow release of ibuprofen. As preliminary study, we just use ibuprofen here as a cheap drug here. And fortunately, our research has been selected as a cover in applied experimental chemistry here. Why we choose graphene or iron nanoparticle here? Yeah? Because the magnesium BTC itself is sensitive to water and also to moisture, and then we can see this through this XRD study. After we expose to the air and the X-ray are changed. That's why we try to combine with graphene oxide to make this more stable, and we choose to combine with iron nanoparticle to have like for targeting the trap. And here we use magnesium here because magnesium is biocompatible and has a positive partial charge that will interact with this ibuprofen electrostatically. We will have electrostatic interaction with the drug. And for drug and the system itself, the interaction is like host and like case and host, through the van der Waals and PP stacking and hydrogen bonding. The weakness of this the system that has been built up is the morphology itself, and the salinity will be lower, and then surface area also. The surface area after the modification hopefully will be increased here. And here we try 3 different approaches. The first approach is how to synthesize the MOF itself, and then the second approach is how to modify this MOF ex situ. Ex situ is when the MOF is built up first, and then modify with this graphene oxide and the iron nanoparticle, and to form the first material. It's when ex situ, and then in situ is when the starting material of the MOF and the graphene oxide and the iron oxide are mixed directly here, with the mixture 1 and mixture 2, and then we put in the sulfate thermal, and we have the material 2 in situ synthesis like that. And we try to these 3 material for loading, the drug loading with ibuprofen in hexane. The hexane we dissolve, the ibuprofen was dissolved in hexane, and then we try to load this material for the ibuprofen, and the precipitate that's resulted from this mixture then wash with hexane, and then we monitor how much the ibuprofen was absorbed by this system. And after that, the release study of this drug from the matrix also studied by taking the solution every 12 hours for 60 hours, around 5 milliliter, and then we make condition for this system in buffer 7.4 and 5.8, and then we calculate the percent release or cumulative percent release of the drug. And here, as you can see, we synthesize 3 material based on magnesium BTC here, and the first material and second material, and here you can see is there is no significantness, or there is no changes, or there is no difference between material 1 and material 2. It means the synthesis in situ and ex situ are successful here, and has no impact of in the material. And then we run also the FTR, and both or the 3 material are still here. 2 are identical here, and the presence of graphene oxide and also this iron nanoparticle are clearly observed here. And here the CEM image here from the material. If here we can see the magnesium BTC itself, and then after we combine with the graphene oxide and also with the iron nanoparticle, they interact each other here. Some are not irregular here, some are irregular here, and some are interact. Mostly the iron nanoparticle are close to this magnesium BTC here, or the MOF itself. But the presence of graphene oxide are mostly outside of this material. The presence of the iron and magnesium here are clearly detected by EDX analysis, and the particle size of the material, the MOF itself is still the larger size. And we try to encapsulate this material with the ibuprofen, and we can detect it how this ibuprofen is already inside. It's by FDR is enough, I think. And we try to load after the loading process, and then we try to release the ibuprofen from the matrix at pH 5 and at pH 7.4, and we can see here clearly that after encapsulating with this matrix, the drug are slowly released here. If you compare with the ibuprofen without matrix here, and at pH 7.4, the release are more explosive or higher than the release at pH 5.0. And what is new in our group here, we try to modify the MIL 101 and MIL 100 Fe. Yeah, the difference is only in the ligand here, because this material after we check several times is very sensitive at acid pH. Yeah. That's why we try to modify this material with silica nanoparticle. How to cover the MOF with silica, or we try to different approach. Yeah, how to cover the silica with MOF, which one is better, and then we will study which composite is nice for application in drug loading and release. And surprisingly, the results are like this. Yeah, sorry. That if we use MOF, yeah, as if we use MOF as core, yeah, we can see here that here is the MOF is in the core here, and silica is outside of the MOF or outer in the MOF. And if we use silica as a core and MOF is outside of the silica, and we will have picture like this. Yeah, the MOF is outside of this silica, and we try to study this the release application, and surprisingly here the left side is at pH 7.4, and at the right is pH 5.8 in the acid condition. And it's clearly seen that if we just have a MOF as a matrix for a drug release, and here is has explosive release or higher release, because it's the MOF itself is sensitive to pH. Yeah. And but if we put the composite based on silica, and then we here the composite one, yeah, it means the MOF is protected by the silica, and it has a slower release. It means the presence of the silica as a composite will protect the MOF from the leaching. Yeah. And here I would say to conclude the talk one. Yeah. That's the release of biosplatin, opiate loading, and the MIL. Yeah, is persistent around 3%, and after we load in the MIL, yeah, it's lower the release speed. It means there's the slow release of the drug is successful here. And if we use the zinc BTC, yeah, which is fully synthesized through the spiral method, and the orthogonal method can produce the higher resil and smaller particle size. And the slowly release of the ibuprofen in the zinc BTC schematic is reached around 33.4, yeah, compared to zinc BTC without matrix. And the presence of composite based on magnesium BTC with graphene oxide or with iron metal nanoparticle prefer and can protect the MOF itself. And the presence of graphene oxide and iron nanoparticle can enhance the graphene absorption. Yeah? And here is the conclusion of the first session. How many time I have still? And here I would like to speak the result in the field of CO2 absorption and inspiration. Yeah. We try also to combine the MOF itself here with zeolite, and also with the polymer or organic polymer for CO2 capture, and also for CO2 expiration here. And for combination with the polymer like polypropylene ethiconate, yeah, we synthesize the polymer, and then we put the polymer itself act as a matrix, and the MOF act as a filler, and we use it as a coating material. Yeah? And then we try to experiment for CO2 absorption, and we use two kind of MOF with H+1, yeah, with copper BTC, and also with MOF 5. And the result is, yes, here the MOF itself still the highest. It has the highest absorption capacity, but and then the addition of MOF into BPA, yeah, after a percent addition, yeah, after around after the addition around 30%, yeah, and the absorption capacity are increased, yeah. And for CO2 absorption, yeah, if we combine the MOF with the zeolite, it means MOF can be exomatric or zeolite can be exomatric. So we try in both in two approach, yeah. If we allow the ionized or activated natural zeolite from near our city, from Yogyakarta, here has the absorption capacity of carbon dioxide around 2.75 millimole per gram, yeah. But after we combine with this type of MOF with 100 FA, the absorption capacity are significantly increased 3 times, yeah, from the initial material. And what's interesting here, yeah, even the crystallinity is not really so high, yeah, because we try to synthesize this MOF in green method in water. The presence of amine group and also the presence of unsaturated metal center in the MOF will catch the carbon dioxide and can increase the absorption capacity. And here, as you can see, that the addition of natural zeolite around 20% in this MOF can have significant enhancement for CO2 absorption. Here we can see around 7 millimole per gram is quite high. Here is the active site for catching for capturing the carbon dioxide. Yeah. And what is related to this capacity is actually about this about the pore surface or pore volume and surface area of the material. After we combine this the two different material, it's mean the zeolite and the MOF, there is adjustment between the pore size and surface area of this material with the carbon dioxide, and the pore size distribution are range from macro to mesopore. Yeah. And here we also try with this with the different kind of MOF with H+1, yeah, and the absorption capacity are still lower, yeah, but lower than the previous composite. Yeah. However, it is also give an enhancement, yeah, around 12%. Yeah. But it's also still nice result, yeah, that can be published. And the nice one here is we can combine also the MOF as filler and with the matrix as polymer, yeah, with the polymer matrix to be used as a hybrid membrane, or we can call it as mixed matrix membrane. And we try to use 3 different MOF here. We use mil 100 Al, yeah, we use aluminum, and then mil 936 Al also, and we try also with mil 53 yeah, Al, and we use polyether solvent as a glassy polymer. And after we of course, for synthesis MOF, we should run the XRD first, and then we check about the porosity of the material. Yeah? And after we mix with this polyether solvent as a polymer, we can see here how the distribution, homogeneity of the MOF distributed into this polymer. This is also not easy job in reality, in the lab. Some agglomeration here are occur, and then we try to optimize the condition and so on. And here we can see here we can see the dense layer from the membrane. Yeah, this come from this the dense layer from the membrane, and then we can see the porous layer that's filled by this MOF itself. And what we can see here, the MOF itself has play important role in catching the gases and also in separating the gases, and also can increase the thermal stability of this composite. We can see this around 50 degrees Celsius. Yeah, this degrees Celsius increasement of this thermal stability of this membrane. and we test the material in ITS in collaboration with Dr. Nurul and Dr. Trianda. And here is the scheme of this instrument for measuring the gas aspiration, and the membrane permeability and membrane selectivity, and then are determined by this equation. And here we have the curve for permeability, the membrane permeability to separate the carbon dioxide, oxygen, and nitrogen gases here, with variation addition of MOF here with mil 53 IL. And we can see here the highest permeability achieved when 30% of mil 53 IL are filled or combined with this PES. And in the case of this is the three trend are the three gases are has the same trend here. I mean, after addition around 30% of this meal, yeah, the permeability are increased here. And for selectivity is vice versa with this permeability, and the selectivity, the highest selectivity are achieved. Is achieved when also the 30% of mil 53 IL are loaded into this PES. Yeah. And if we compare the result in the Robinson curve here, we can see here our result are still lower than the Robinson curve, but at least still higher than this PES itself. Yeah, the blue. Yeah, PES here, and here is the addition of the MOF. It means the addition of MOF still have impact. Yeah, make impact in this gas aspiration. And if we see here is in the case of carbon dioxide and nitrogen, and in the case of oxygen and nitrogen, we plot this result also into the Robinson curve, and still here the addition of the MOF still have better performance than the PES itself, but in the Robinson are still under the curve. Yes. And what's interesting here, if we try to test this mixed metallic membrane to separate this hydrogen and carbon dioxide and hydrogen and methane, the results are higher than the Robinson curve here. It is a nice result. And also in the case of hydrogen and methane here for the aspiration, the loading of mil 553 AL, so this upper than the Robinson curve. That's why this also a nice result that presented by this mixed metallic membrane that we have. And after here, maybe I will conclude the study of this MOF for after we compositing with some material like zeolite or with organic polymer. In the application of absorption has a promising result, and it's been will promising also for the growing application. Yeah. And then the absorption capacity of composite mil 100 FA with natural zeolite. Yeah. So 3 time enhancement after the addition of 2% weight, which reach up to 7 millimole per gram. And then the loading of mil 53 AL, yeah, for 4% into PES can affect the resulting NMS characteristic, as an increase in thermal stability around 50 degrees Celsius, and then the addition of 30%, yeah, 30% weight of mil 53 AL can increase also the permeability value of nitrogen gases, nitrogen, oxygen, and carbon dioxide gases. Yeah. Until here is 8 times. Yeah, it's 8 times. And the gas aspiration performance for CO2 and oxygen is the maximum value, the variation of 40% addition of the mil 53, yeah, and can increase around 26.7 compared to the PES membrane. And the permeability of hydrogen gases can also increase the addition of 20% of mil, and as you can see that we can suppress this curve Robinson, yeah, and we can be in the upper position of the Robinson curve. Yes, maybe it's the end of our talk, and then many thanks, and I would like to thanks for the collaboration and also for the hard work from my student here that support my research, and also from the sponsor that give funding for my research. And thank you very much for your kind attention.
Okay, thank you very much, Dr. Witri, for your excellent presentations. We can see, from the beginning, Dr. Witri introduced to us many kind of the composite system, especially regarding to the preparations of coordinating porous material. Yeah, even she employs many, I guess, many precursors, not only the variety of the organic linker, but also the different metal ions. Yeah, also in her work, I guess more than 10 research work here that's been presented. She even employ many type of modifiers such as silica, yeah, and then zeolite, graphene oxide, and even though organic polymers. She also shared with us about several types of application that can be made with the developed materials based on MOF, yeah, for drug delivery, for drug release, even though for bioimaging, and for cancer therapy, and the last one for the carbon dioxide capture and any gas absorption. Thank you, Dr. Witri, for your great presentation. And I do believe as our participants still keep the questions, so please kindly write down your questions, comment to the speakers that been presented their work here. And then please kindly wait for all participants to have direct discussions with all speakers, because we still have the third invited speaker here. Okay, very good afternoon, Pak Grandprix. I guess you still unmute your audio.
Yeah. Can you hear me clearly?
Oh, sure. Yeah, your voice now is great. Yeah, Dr. Grandprix, actually, I've been invited you for other occasions on 2017, if I'm not mistaken. At that time, you were away, and then you delivered the presentation online for around 7,000 participants at the time. We organized really great seminar.
I still do remember.
Yeah.
Thank you.
So yeah, again, thank you so much for your great availability. Again, it's really happy for me. Finally, we have another great connections here through the seminar. And for all of participants here, I would like to greatly introduce our third speaker. He is actually the young great scientist of Indonesia, I guess. Now he affiliated to Institute Technology Bandung. Yeah, here I would like to introduce Dr. Grandprix briefly. Actually, his name is very unique. Everyone, if you go to the Google Scholar or Scopus, yeah. But one time you put Grandprix, then yeah, his photo will be appear. So he graduated for master and doctoral degree from Institute Technology of Bandung, yeah. And then now he affiliated to the inorganic and physical chemistry group, especially in the catalyst center. Can you move back? If you move back, yeah. And then also, I guess he has some activities in the nanoscience and nanotechnology research center in Institute Technology Bandung. And then here I would like also to introduce to all participants about his current research work, yeah, in ITB. Especially he focusing on designing, synthesizing, and even though development material, yeah, regarding to the functionalizations and also material characterizations on the nanoporous and nanosheet material. And here in this study, I also been checked in his current publication, also working in the how to say inorganic polymer composite system, yeah, and hopefully today he can share with us, yeah, in this presentation. And also he's really inspiring, I guess, for all of us. He received many awards regarding to his achievement during his study, I guess, as well as his current work. Yeah, he is one of the young maybe the chemist youngest doctor in Indonesia, yeah, through the special program offered by our ministry.
of education at that time and higher education. And also he was the best graduate of Department of Chemistry in Universitas Indonesia, maybe for his undergraduate program, right?
Yeah.
And also the winner of Pertamina Science Project and silver medal for mathematics and science Olympiad. So without any further ado, Dr. Grandprix, time and place is yours.
Thank you, Dr. Witri, for your kind invitation. I would like to share my screen. Wait. Yep. Can you
Yeah.
see the?
Yeah, it's perfect. It's perfect.
Okay, thank you.
You just need to slideshow.
Yep.
Yeah.
Okay. Good afternoon, ladies and gentlemen. I would like to express my gratitude first to the Universitas Pendidikan Indonesia, especially for Dr. Witri, who have been kindly invite me to this occasion, to this good occasion, and I would like to greet Professor Opaprakasit and Dr. Witri. Dr. Witri is one of my collaborator, one of the closest collaborator. Thank you very much for this very good occasion, and in this opportunity, I would like to share regarding the recent advances on the polymer inorganic nanocomposites for membrane applications. But my talk may be from the inorganic point of view, because as have been mentioned by Dr. Witri, I'm from the inorganic and physical chemistry division. I'm from Institut Teknologi Bandung, located in the West Java, Indonesia. We are the oldest science and technological institute in Indonesia, and last year we just celebrated our centennial anniversary. So in this year, in 2021, we have been 101 years young. This is our group. This is 2019, before the pandemic, in which we could made an offline meeting, but this is us during the pandemic. We meet virtually. If you want to know better about our research group, you can visit our website at kadjalab.com. If you're interested, please do so. And our research focus mainly on the nanolayered and nanoporous materials. I would like to, in this presentation, I will talk about the Maxan, the zeolite, especially in the separation application. We also work on the mesoporous aluminosilica as well as MOF and COF. Especially on Maxan and MOF and COF, we just started. Dr. Witri have provided us with many of MOF samples, but currently we are working on this research area, nanolayered and nanoporous materials. So I would like to move on to my talk regarding the polymeric and inorganic nanocomposite for membrane applications. So I would like to start with the polymeric membranes. As we have already known that membrane is a semi-permeable barrier that allows the selective passage of certain species, meanwhile retain others. So it basically depends on the selectivity. So polymeric membranes, it straightly means that the membranes are composed of polymeric materials. You can see here, this is the SEM image of polymeric membranes. You can see when we observe the cross section, it will show us the porosity that will act as the molecular shift. and this is the top view in which the surface is relatively smooth. It has at least 4 separation mechanisms, as you can see here. It is based on the size exclusion, in which it is acting as the molecular sieve or the particle sieve. It could also function based on the electrostatic repulsion, based on the interaction. If we have the same electrical charge, then the molecules will be repelled. But if the molecules and the membrane surface, they have a different charge, and then the molecules will be attracted to the membrane surface. It could also based on the adsorption, in which we could classify into subclasses, which is the hydrophobic interaction and the fouling layer interaction. But I would say among these 4 mechanisms, the size exclusion and electrostatic repulsion would be the main mechanism in the separation of within the membrane. However, there are many challenges in the polymeric membranes. One of the most discussed, one of the biggest issue in the use of polymeric membranes, it is the trade-off issue. You can see here that if we plot the selectivity versus the permeability, as you know, the selectivity and permeability are the 2 main factors in the separation performance. The conventional polymer membranes have a trade-off issue. If we have a highly selective membrane, the permeability will be very low. On the other hand, if we have such a high permeability, the selectivity will be damaged. So this is the trade-off issue within the polymeric membranes. Dr. Witri has mentioned regarding the Robinson upper bound line here. This is the upper limit of the separation performance of polymeric membranes. But in the practical use, we would like to be in this region. We would like to have a high selectivity as well as high permeability. But if we use the pristine polymeric membranes, we could not achieve this target region. The same case also appeared in the water separation. As you can see here, it also exhibits the trade-off issue. We cannot have high selectivity with high permeability. So we have to choose between one of the 2 factors. On the other hand, we could also move to the inorganic membranes. In this case, I would like to focus on zeolites. If you have not been familiar with zeolites, zeolites are classified as microporous. The pore size distribution is below 2 nanometers. They are microporous aluminosilicate crystalline materials. So it has uniform distribution of micropores, as you can see here in the TEM image. It has large surface area. You can see here that the 1 gram of zeolite has a pore length of 6 times 10 to the power of 11 meter, which is 4 times the distance from Earth to the Sun. So it has large surface area. It has uniform distribution of micropores that could act as a separation layer, which is a membrane. There are 3 main properties of zeolite, which is the ion exchange ability. It has the formal charge of zeolite backbone is negative charge. It is negatively charged because the tetrahedral silicon is isomorphically substituted with tetrahedral aluminum. So we know that the silicon has zero formal charge. If we substitute it with the aluminum tetrahedra has a -1 formal charge. So the zeolite will be negatively charged, and it has strong acidity. But this is not relevant in the separation application. It will be relevant if we apply zeolite as a catalyst. So these two properties are desired for the membrane applications. If we talk about the inorganic membranes, especially zeolite, we would encounter with the polycrystalline layer, which are grown on a macroporous support. Commonly, it is a microporous alumina or macroporous silica. Of course, the support does not have the separation capabilities, but it is used to support the zeolite layer, because the zeolite layer is rigid, it is polycrystalline, it cannot withstand harsh condition. For example, high temperature. Of course, high temperature zeolite can withstand, but the high pressure, the zeolite layer cannot withstand the high pressure. So we can see here, this is the comparisons between the polymeric and inorganic membranes. The polymeric membranes has their advantages and disadvantages, and the same cases also appear in the organic membranes. For example, inorganic membranes, they have, for example, zeolite, they have better separation performance. They have better permeability, and they have better selectivity compared to those of polymeric membranes. But on the other hand, they are fragile and rigid. Unlike the polymer that have flexible properties or the elastic properties. So there are weaknesses, there are advantages. So how do we choose between them, between polymeric and inorganic membranes? In fact, we do not have to choose between polymeric and inorganic membranes, because we can just combine them. So the advantages of the zeolite will offset the disadvantages of polymeric membranes. On the other hand, the advantages of polymeric membranes will overcome the disadvantages of inorganic membranes. So when we combine the polymeric and inorganic membranes, we will obtain a novel materials that is called mixed matrix membrane. So a mixed matrix membrane is the incorporation of solid phase, which is the inorganic materials, in a continuous layer of polymer. So to put it simply, we just disperse our inorganic fillers within the continuous layers of polymers. As we can see here, as I have mentioned before, inorganic membranes, they have better separation performance compared to those of the polymers. They are high above the Robinson upper bound limit. But if we combine the inorganic and organic polymers into mixed matrix membranes or MMMs, we could, the performance is slightly below the inorganic membranes, but the technical disadvantages within the inorganic membranes can be offset, can be compensated by the polymers. As you can see here, also the separation performance of MMMs are above the upper bound limit, and it is placed in the commercially interesting area or in the turgid region. However, combining inorganic with the polymeric membranes is not as easy as it sounds. Here we can see that if we combine the inorganic filler with the polymeric membranes, the ideal case will be like this. The continuous phase, the polymer phase, will well interact with the dispersed phase or the inorganic filler. There is no empty space between the surface of zeolite or the inorganic filler with the continuous phase of polymers. This is the ideal case. They are compatible. But often we have this incompatible cases in which, for example here, there will be interfacial voids. There will be empty spaces, empty voids between or within the interface of zeolite or inorganic fillers and the polymers. What is the disadvantage of this case? As you can see here, the permeability will increase, of course, because we have such gigantic voids over there, but the selectivity will be damaged. It will be significantly reduced because we have such a big hole within the interfacial. On the other hand, we could also encounter with these two cases, the rigidified polymer or the pore blockage. The rigidified polymer means the polymer with in the interface of zeolite will be rigidified. They will lose the porosity. So if the porosity are eliminated, then the separation performance are also decreased. As you can see here, the consequence is if I have the molecule, let's say oxygen or carbon dioxide, it could penetrate the continuous phase of the polymers, but it cannot enter the inorganic fillers. Why? Because the layer, the interfacial layer here, has lost their porosity. So there is no need, there is no use of the inorganic fillers because the molecules cannot enter. The same case is also found in here, the pore blockage. They are similar, but the pore blockage means that the porosity has been completely gone, has been completely eliminated. That's why if we have the pore blockage or the rigidified polymer, in the rigidified polymer, the selectivity could be increased, but the permeability is decreased essentially. But if the pore blockage occurs, the selectivity stays the same, but the permeability is reduced. So we don't want these three cases. We want this ideal case. So how to obtain the ideal case? We have several strategies, at least two strategies. We have to use the bridging agents. What is the bridging agents? The agents to facilitate the interaction between the polymer phase and the inorganic phase. And in doing so, the bridging agents could be inorganic, could also be organic. For example, here, we use the inorganic bridging agents. This is the zeolite, which will be function as the inorganic filler. We could grow the nanoparticles in this case, the magnesium hydroxide nanoparticles, to form such a unique morphology, the nanorod morphology on the surface of zeolite, which will be function as an anchor. So the polymeric phase will surround the interface, and then they will be anchored to this newly grown nanoparticles. So we can facilitate the interaction between zeolite and the polymer phase. On the other hand, we could use the organic bridging agents. In this sense, we will use the organosilane. As you can see here, for example, this is the organosilane that we use, the aminopropyl 3-methoxysilane. The silane will react with the terminal silanol to form the new siloxane bond. It will form a new covalent bondings between the bridge and the inorganic phase, and this alkyl groups will interact with the polymer chain. So here is the example. If we do not use the bridging agents, the aptes, there will be interfacial voids because the interaction is not good. But after we use the bridging agent, the aptes, the voids are now closed because the polymer has been well interacted with the inorganic phase. So these are the two strategies that we use to obtain ideal MMMs. Okay, now I would like to move on to the recent advances in the polymer and inorganic nanocomposite membranes from the inorganic point of view. As I have mentioned before, inorganic membranes, they are based on polycrystalline layers. But this polycrystalline layer, they have their own weaknesses. Because they are polycrystalline, they are made of many crystals, they could have many defects. For example, this intercrystalline spore, which has such a larger size that will allow the transport of any molecules on the in other words, it will damage the selectivity of the inorganic membranes. There are many defects, for example, the ground boundary, the intercrystalline pore, the pinhole, and so on, because they are polycrystalline in nature. But these weaknesses could be eliminated if we reduce the size into the nanoscale. We can see here that if we have such a continuous layer with minimum thickness, we could eliminate the weaknesses in the conventional inorganic membranes. As you can see here, this is the example of nano-sheet zeolites, in which it has, or I could say, the atomic thickness, 1.5 nanometers. This is the single cell of a zeolite, crystals. If we could synthesize these nano-sheet zeolites with large lateral dimension, we could have such a quote-unquote perfect separation performance. We can see here, we could then use the nano-sheet inorganic fillers to create the novel mixed matrix membranes. As you can see here, if we have the stackings or the stacks of nanosheet inorganic fillers, it could create a new or abundant intergalleries or interplanar spacings, which could give a tortuosity, then act as separating layers. For example, the two adjacents layers or the two adjacent nanosheet could create a new porosity. That's why the nanosheet or even the dense nanosheet, the non-porous nanosheet, could act as a membrane. And the separation performance could also be increased if we use the nanoporous nanosheets, for example, the zeolites. Now I would like to talk about several types of those nanosheets in organic materials. For example, the first one is graphene-based membranes. So many of you may have been familiar with graphenes. Graphene, actually the single layer that form the graphite, one of the carbon allotrope. So this is the graphene. If when we exfoliate the graphene layer from the graphite, we could use these several methods, which the four of them are oxidative routes. So when we oxidize them, the graphene could be converted into these materials that we call graphene oxides, because now we have several oxygen containing functional groups. For example, carboxylic acid, we will have alcohol groups, epoxy groups, and so on and so on. And for your information, graphene are dense materials. They do not have pores within them. But as you can see, when we stack several layers of graphenes, it will create new tortuosity or new interplanar spacing that will act as the separating layers. This is an example when we combine graphene oxide with the PSF, the polysulfone membranes. We cannot distinguish them just based on the SEM, because it will appears to be the same. But when we tested them as the membranes for carbon dioxide and nitrogen, and carbon dioxide and methane separating membrane, we could see that the pristine polymeric membrane, the selectivity for carbon dioxide and nitrogen is only 17. But when we incorporate graphene oxide within the continuous layer of polysulfone, the selectivity is dramatically increased to 44. The same case also happened to carbon dioxide and methane mixtures. When we incorporate graphene oxide, the selectivity is also increased more around 2 times, around 2 times higher than in the pristine polysulfone. Not only the selectivity is increased, as you can see, the permeability is also increased as well. That's why we have broken the thread of issue. We have broken the thread of issue just by incorporating the nanosheet inorganic fillers. So you can see here, this is the proposed mechanism for the separation within the graphene oxide polysulfone mixed matrix membranes. As I've mentioned before, this is the layer of graphene horizontally aligned. It could create new interplanar spacing, act as a separating membrane or separating layer. but we cannot control the orientation of the nanoseed layers within the continuous phase of polymers. But it would not be a problem. Why? Because either horizontally aligned or vertically aligned, they could well act as the separating layers. Why? Because it just imagine if we have nanoseed layers with vertical alignment, it could also create a channel, a nano channels. So it doesn't matter if the nanoseeds are horizontally or vertically aligned. Both alignment can be used to separate the molecules. So there is the another advantage of nanoseed inorganic filler. This is the second type of dense nanoseed that we could use. It's called Maxen. Maybe some of you have been familiar, but I believe many of you may have not been familiar with these materials because it was discovered in 2011, around 10 years ago. So one of the novel materials. It is based on the mix phases. So mix means we have inorganic materials that are formed by 3 layers. The M layer is the early transition metals. The A layer is the A group elements, and the X is the halide, or not the halide, but the carbon or nitrogen group elements. So for example, we would have the titanium, aluminum carbide, or titanium, aluminum nitride. So based on this 3 layers. If we eliminate, if we etch the second layer, for example, we etch the aluminum using the hydrofluoric acid, we could eliminate, we could dissolve the second layer, and we could obtain the nanoseed based on the MX layers. So for example, if we have titanium aluminum carbide, we etch the aluminum, we could get the titanium carbide nanoseed. For example, here, we will have the titanium aluminum carbide. We etch them, we etch the aluminum layer using the in situ HF formation. So we would have this one, the nice nanoseed layers. This is the morphology of the max phase, and this is the morphology after we etch the aluminum layers. So why is the name Maxen? So the suffix N is inspired by the graphene. So it would be awkward to say just MX. So why don't we put the N suffix just to make it sound like graphene? Because it has the similar properties to those of graphenes. So that's why it is called Maxen. As I have mentioned before, the properties are similar to those of graphenes, but the difference is that it contains titanium, which would give high conductivity, and it will be an advantage for other application, for example, sensor, photocatalyst, and so on. This is the examples when we incorporate Maxen within the chitosan polymers. When we incorporate more Maxen, we could have a rougher surface, indicating the incorporation of Maxen has been successful. And the application in the pervaporation, for example, here the water and ethyl acetate mixtures and water and dimethyl carbonate mixtures. the presence of MXN, again, it increases the flux or the permeability as well as the selectivity. Once again, we have broken the trade-off issue because we increase both of the separation factors, which are flux or permeability and the selectivity or the separation factors. This case is also found in other mixtures, which is the water and dimethyl carbonate. The incorporation of MXNs does increase the flux and the separation factor. Why? Because again, MXN have separation properties thanks to their unique morphology, the nanosheet structure. And the last one is zeolite nanosheet-based membranes. Actually, the MOF and COF can also be incorporated as nanosheet membranes or a nanosheet or filler, but I would not include in this talk because it has been well covered by Witri. But as you can see here, we could synthesize the nanosheet zeolites. We could observe the morphology clearly to SEM, TEM, and AFM. We could vary the zeolite content within the zeolite PBEX MMMs. The PBEX is polyether block polymers. As you can see here, if we increase the zeolite content to 5%, the morphology are still smooth. The zeolite nanosheet are well dispersed. But if we increase to 7%, we could encounter the agglomerated nanosheets because the content is too much, I guess. So the optimum content of zeolite is 5% within the PBEX MMs. And we could see here in the separation application for carbon dioxide and methane gas mixtures, the increment of zeolite loading does increase the permeability and selectivity. Again, we've broken the trade-off issue. We could simultaneously increase the permeability and the selectivity. But the opposite trend is found when the zeolite loading is 7%. This is due to the agglomeration of the nanosheets, which is undesired because it will create such defects that, of course, will damage the separation application. So I have shown you the 3 examples that the incorporation of nanosheet organic filler could increase simultaneously the permeability and selectivity of a polymer membrane. As you can see here, PBEX is considered as, how to say, not really good polymeric membranes for carbon dioxide and methane separation. It lies down below the upper bound. But just because we have incorporated the zeolite nanosheet membrane or the zeolite nanosheet fillers, now the separation performance could be increased above the upper bound. So you have already seen how the nanosheet inorganic filler could dramatically increase the performance of polymer that is considered bad for this application. So here is the difference between the graphene and MXN and the zeolite, MOF, and COF separation mechanism. So the graphene and MXN are dense nanosheets, it performs the separation based on the interlayer spacings, while the zeolite, MOF, and COF, in addition to the interlayer spacing, it has an intrinsic porosity that will further increase the separation performance. This is the advantages and disadvantages, as well as the opportunities to further develop the nanosheet membranes. It will be published soon. And it is the last part of my talk, the outlook of this topic. The combination of polymeric and inorganic membranes are strictly needed to overcome issues in both pristine materials, to overcome the trade-off issue, to overcome the rigidity issue, and so on. Several strategies have been proposed to create an ideal mixed matrix membranes. From the inorganics viewpoint, the use of nanosheet morphology should significantly improve the separation performance due to the unique physicochemical properties, and it could provide a new separation mechanism. It is imperative to develop graphene and mexene with introduced nanopores because they are dense nanosheets. If we could introduce an intrinsic nanopores within the mexene or graphene layers, it would be much better. It would have much better separation performance, and it could operate under high operating pressure. And the last point is to realize the industrially relevant nanosheet membranes, they need to be mass produced. In this sense, we must ensure that the properties and separation performance of nanosheet membranes does not fall significantly from those synthesized on a lab scale. So we have to mass produce the membranes, but the performance should stay the same, should be consistent. And these are the two recommended books or chapter books if you want to learn more on these topics. This is published in 2020 in chapter 11. This is our chapter book regarding the modified zeolite-based polymer nanocomposite membranes. And this is the newly upcoming books we have contributed in one of the chapters with Bu Witri regarding the advanced ordered nanoporous materials. I would like to acknowledge the funders who have financially support our research, and of course to all the students who have put hard work to realize all of the results. Thank you very much for your attention.
All right, thank you so much, Dr. Grandprix, for your interesting materials, and also interesting talk and systematic talks. I guess all audience can learn easily how to understand this is, I guess, a current innovations, on developing the membranes materials based on the nanolayer, nanoporous materials. So you show us the great example how how to develop the composite system based on the polymeric and also inorganic materials in order to prevent, to overcome the obstacle in terms of trade-off issue regarding to the selectivity and also permeability. Also, you provide us the great example of the unique system. You said mixed matrix membranes, but if I may call it a kind of triple M system. It's really unique, and the characters is just follow like the graphene system, in which it greatly contributes to the performance of the membrane. And you also provide us the great information about the strategy how to meet the good membrane system that can be passed from the trade-off issue, with the bridgings by utilize inorganic and organic systems, into your composite membrane. And I do believe many participants here still keep the questions to your presentations. And thank you again, Dr. Grandprix. And all participants, finally we come to the last sessions of this seminar. It is the Q&A sessions, and I captured some questions, several questions come from the audience, and to all the invited speaker, I try to summarize the questions and also maybe comment from the participants. So Prof. Pakkorn, as well Dr. Witri and also Dr. Grandprix, here is the questions, maybe some typical questions to certain participant, and could be maybe you can respond as well. Here the first questions for Prof. Pakkorn. So it's come from Asep Bustani from Laboratory of Technology for Polymer in BPPT. This is one of the, how to say, research institute, that we have in national level. The question is how to prove the degradable polymer is more suitable in terms of circular economy compared to the conventional polymer. Please,
Okay.
Prof. Pakkorn.
So thank you very much. To answer that questions, I would say we may not be able to tell which one more suitable. Or I mean that degradable polymer are definitely more suitable. It still depends on some technology or some process that we apply to the post-consumer products, right? So the main concept of circular economy means we can take the product after use or post-consumer products and then convert them into new products that still have good quality and also still have high value, right? So for conventional polymer, usually conventional polymer are made from petroleum-based resources or monomers. One of the problem with that is the supply for petroleum, right, or crude oils may not be so much anymore. It will be running out very soon. So in the future, we may not have raw material, right, for making petroleum-based polymers, right? In contrast, if we talk about degradable polymer, the majority of degradable polymers are renewable or come from bio-based. It can be made from plants or from animals, right? Somehow like chitin or chitosan. So this can be, we do have a continuous supply from this, right? It is sustainable choice. So that also can add up to another criteria that we can consider, like the degradable polymer may be more suitable into the circular economy concept, right? But in the future, right, the main concern about recycling now, like mechanical recycling, is once we need to melt the polymer in order to make them into new products, right? But anytime we heat polymer up to high temperature, there will be some problem. The chain will break, right? So when chain break, polymer is very long. If there is only one point break in the chain, the molecular weight reduced to half, right? That significantly affect the properties of the polymers, right? But in the future, if we can have a mechanism that can prevent this degradation of the chain, right? Maybe that is still suitable for circularity of the polymers, right? But for now, I think the technology that we have, we can apply to break chain of degradable polymer and make them into new material or small size products, right, that can be converted later on into new polymer. This may be more more promising than than the conventional polymers, right? I think to address this question, I think this may give more information to support right?
Yeah, that's right. Pak Asep, hopefully it answer your questions. If you still have any, you can raise your hand, and then we can continue firstly to the second questions. It's come from Habib Aziz. Still the question for Prof. Pakkorn. First question is, how do we identify whether a poly is biodegradable or not? And secondly, which one is easier, designing a biodegradable or bioengineering a microbe that can digest a polymer?
I see. I see.
Please, Prof. Pakkorn.
Okay, so let me share the screen again. So if we look at this picture right here, right? So degradable polymers, right? The majority of them should have this functional group, ester group, and we know that ester is made from acid, right? And alcohol. And we know that when this react, it will generate ester bond. And this ester bond, right? Once it's generated, it also can break as well. So this reaction is actually reversible, right, by water. Right? So that is for small molecule. But for polymer, this is very long chain. Right? For water to get access into this ester bond, right, it may be harder, right, compared to small molecule. Right? But if it is possible, right, if water can get to the ester bond, it have potential, right, to break the bond. Right? That is the main reason we can make polymer degrade. Right? So the majority of polymer are polyester. Right? The majority of degradable polymer are polyester, containing ester bond in the chain. Compared to, right, polyolefin that have only carbon-carbon bond. This carbon-carbon bond is very strong, right? It is very hard, right, to break them. So therefore, polymer that contain only CC bond in the chain will not be degradable. Right? So that probably answered the first question. The second question is, what is it?
There is some noise.
Okay, so which one is easier to design, like biodegradable or design microbe to eat the polymer?
Yeah.
Actually, there are some research that work on designing microbe to degrade this polyolefin polymer. Right? Actually, for polyester, they are biodegradable. They can be degraded from normal microbe that we see in nature. Right? So they can be degradable in nature. Right? But for polyolefin here, there are some type of microbe that can work on this. However, I would say if we want to do bioengineering to create new type of microbe, it also have some risk as well, right? How do we know that if there is no mutation to that microbe and then can cause other serious problem, something like this, right? But at this moment, in contrast, we have established technology to make degradable polymer, and many of them are commercially available already. Right? I would say making or develop new type of degradable may be more promising than developing new type of microbe, right? By bioengineering.
Yeah, like the COVID-19, Prof. It developed so fast with the different type of the virus. Yeah, it's also almost uncontrollable. Yeah, I almost agree with your opinion.
Right.
So okay, thank you so much, Prof. Pakkorn, for
and the last question.
Yeah, the last questions we still have.
The last question, PLA is degradable, right?
That's one.
How do we know that it's safe enough, right?
Yeah.
For food contact or beverage packaging.
Yes.
Actually, PLA is proven that it is biocompatible. PLA is made from lactic acid. Lactic acid, right, can be produced in our body as well, right? By cell respiration process, right? The toxicity of polymer is actually come from the component that have small size, right? If we can make polymer to have very big molecule, right, very high molecular weight, it doesn't matter what type of polymer, they should be biocompatible, not non-toxic, right? So the toxic part that come from polymer product usually come from small size molecule that are in the polymer products, right? But in this case, if PLA degrade, right, it degrade into small size product that is called lactic acid, the original monomer. The lactic acid here is not toxic to the cell, right? Therefore, it is safe, right, to use PLA in food contact application, even though during the storage time we may have some degradation happen, right? It is still safe, right? But maybe the appearance may not be so good, or mechanical properties may not be suitable. That is another problems, right? But for the safety, it is still safe.
It is safe, yeah, due to the compatibility, yeah.
Right.
Okay, thank you, Prof. Pakkorn, for your answer. And then we try to move. Prof. Pakkorn, could you please? Yeah, thank you. And then here we move to the next questions. I guess some questions for Dr. Witri. First questions come from Adam Nugraha. What should we consider once we want to synthesize MO with the hybrid linker in so different dimensional measure? Yeah, for example, linker length or diameter of each MOF, if they are synthesized individually in order to avoid the MOF structures collapse.
Yes, thank you for the question. It's the smart question. Yeah? Actually, the first consideration, if we want to have like stable MOF, not easy collapse MOFs like that, is the factor is the option or the choice of the metal itself, because some metals that have like high valence, like 3+ or 4+, is more stable to this air or water or moisture. And about the linker itself, it's various. Yeah. In my opinion, during my PhD, I synthesized a long linker, very long linker, and highly modified with phosphorus, something like that. We actually want to have like stable MOF and rigid MOF, but at the end we have like collapse MOF, and we cannot use for catalytic action because the linker is too high and also flexible. This one, it's better is to avoid the flexible actually, but it's come back again to this what we want to have for application. For example, for breathing MOF or MOF that can move, also good for gas comparison, something like that. But for too long linker, some problem might occur, something like interpenetration, because if one framework to another framework is physically interact, and they can make like interpreting network, and it will block the pore, something like that. Yeah, sometimes the scientists also do like computational job first to screening the linker and screening what metal is suitable for the MOFs. That's why to create a new MOF, especially a novel MOF with novel linker, is also a good challenge in my opinion. Yeah.
So means still many great opportunity, yeah, to challenge for finding the combinations between the best metal ion and also linker, yeah.
Yes,
Oh,
yes. But the metal ion with high valence like zirconium is mostly are stable.
Oh,
Yeah.
yeah.
Zirconium, aluminum, something like that, mostly are stable. Yeah.
Yeah, so the valence of the metal ion is the most
Yes.
considerations, yeah, for that one.
Yeah, yes.
Okay, I guess the questions is already answered, and then the second questions is from Habib. Yep, many questions. First, how are coke and mops different in terms of physical and mechanical properties? Yeah, is there any coke that is purely hydrocarbon? And then the next question is when you incorporate. Oh, this is for
This is
Dr.
for
Grandprix.
Dr.
Okay,
Grandprix,
okay.
number
Okay,
three.
just
Yes.
I mentioned the questions, and after Bu Witri reply the question, so it can be moved to Dr. Grandprix, yeah,
Okay.
to
Okay.
reply the third question. When you incorporate
Yes.
mixin to chitosan, the surface is remarkably rugged. So I wonder, will it affect the polling significantly? Please, Dr. Witri, firstly.
Yes, actually the difference between MOF and COF is in the nodes. Yeah, if we synthesize MOF, we use a metal ion or metal oxide cluster as a node, and then we connect with organic linker. But in the case of COF, we use purely organic nodes like boronic acid or amine, yeah, and then like acid and something like that, and sometimes also fluoride, yeah. And then connected to some GC bond, yeah, purely organic like that. And about the physical and mechanical properties, actually both are also good. Yeah, both are has a good stability until around 900 degrees Celsius, I think. And what else? And also both has good porosity also. Yeah.
Okay.
And is it purely hydrocarbon? I would say no, because it consists of boron also, and also amine, and also some are fluorine. Yeah.
So not only carbon and hydrogen.
Yeah, not only
the
carbon and
structures.
hydrogen.
That's
Yes.
right.
May I interrupt? I have one
Sure.
question for Dr.
Witri.
Witri.
Oh, please,
Yes.
Prof.
Yes.
This
Yeah.
is, yeah.
In the system that you have for carbon dioxide capture,
Yes.
right? And could you also comment on the utilization of the capture CO2 and the desorption process and the utilization?
The utilization, we still do not have further research about that. We still on the step of capture and expiration. Maybe in the future we would like to do this research, yeah, with Dr. Grandprix. Last 2 months we have a guest lecture from Thailand State University. Yeah, they do like utilization of carbon dioxide to be useful compounds. Yeah, this one also still a challenge.
Okay.
Maybe in your group, Professor Pakkorn, are you working also with this research?
Yeah, we are interested in some part of that. We conduct some like only prelim work, but maybe it is very interesting to continue in the future.
Yes.
Since many variety of the mob structures, yeah, that can be made with a certain applications. Okay, I guess Dr. Witri already answered the question from Hafiz. And then please, Dr. Grandprix, no issue.
Yeah, thank you for the question about the fouling on Mexan chitosan mixed matrix membranes. Maybe it can be due to the roughness of the surface. Maybe it can cause membrane fouling. But as I've mentioned before, the application that I have shown on the Mexan chitosan mixed matrix membranes, it is on the gas separation, not on the water separation. So the membrane fouling might not be significant as in the water separation. But one thing that I can say is that membrane fouling happens because there is a strong affinity between the molecules and the membrane surface. So the strategy that we could perform is that the interaction between our membrane and the molecules should not be so strong. In this sense, we could, perform the surface treatment or surface modification and so on to prevent the occurrence of membrane falling. In the case of sense, because it is highly the surface is highly hydrophilic because it contains fluorine, oxygen, hydroxyl. Functional groups. Maybe we will, if we do not perform the surface modification, maybe we could select the molecules that is less hydrophilic so that it cannot interact so strong. Thank you.
Okay, thank you, Dr. Grandprix, for your answer. And still, we have around several minutes before we close this seminar session. So still I invite a participant who still want to deliver questions or comment to our invited speaker. You can raise a hand and then open your mic directly, if any, please. We have many great information today, Prof. Pakkorn, Dr. Witri, and Dr. Grandprix. Thank you so much for kindly providing us really, how to say, excellent work, yeah, and as well the great example of your developed materials. I guess it will be inspiring for all of us here. And then please, for audience, if you still have any questions, we are very welcome to have any voice from all of you. Or the previous speaker, if you still have any curiosity to continue your questions, Adam or Hafiz or other participants, please. Oh, Mita, no? All right, I guess everyone is quite tired with the long presentations, but yeah, this is very special occasions in which we can meet together with the great speaker, yeah, within one frame. So again, Prof. Pakkorn, Dr. Witri, and as well Dr. Grandprix, thank you so much. We would like to, how to say, thanks for your great and excellent contributions on our first seminar. On behalf of the committee of this seminar, we already provide the certificate for your presentation. So firstly here for Prof. Pakkorn, and then secondly for Dr. Witri, and thirdly for Dr. Grandprix. Some participants request your PowerPoint presentation if you are not, if you don't mind to share with the participants. So maybe later on, I will contact you further through email or WhatsApp to ask your PowerPoint presentations. And for the participants who require for the attendance certificate, please kindly fulfill your information through this link. Yeah, we provide here on the screen and also maybe in the chat box. So please kindly write down your information to provide your e-certificate. And another information is, as I mentioned on the beginning of this seminar, we still have other series of the seminar organizing by World Class Professor Program. So the second seminar, we will provide another talk still related to the polymer and composite. Yeah. And Prof. Pakkorn will be still with us, but of course with the different topic. He still have many interesting topics to be shared with you. And the second speaker, we will have Prof. Sang-Yeon Lee from Kyungpook National University of Korea, and he would share with us about the forward osmosis technology. And thirdly, we will have another colleagues from LIPI or Indonesian Institute of Science. He also graduated from Korea, if I'm not mistaken, and also he had some former project in the KAIS, yeah, when maybe he studied there. And in this moment, he will share about the biopolymer composite processing, especially on the wood. yeah, wood processing with some copolymerization. So through this flyer, please kindly how to say register yourself if you would like to join again with our seminar and it would be very welcome to have you again, yeah, come back to our second seminar. And I guess that's all our informations. And maybe before we close this session, maybe everyone can open your camera and then we can have the great picture with our beloved speaker today, if possible, yeah. And then the committee will take your pictures and then we will share, yeah, the photos to all of you through the email, of course, or the contact that you provided for us. So please, Prof. Pakkorn, Dr. Grandprix, Dr. Witri, we would like to take all of us pictures. Everyone ready? Okay, I will count from 3, 2, 1. All right, nice. And then another layer, please. 3, 2, 1. Okay, where's your smile? Actually, it's already 4 p.m. Yeah. Okay, 1, 2, 3. All right, and the last one, I guess. 1, 2, 3. All right, nice. Thank you again. Thank you so much to all participants and especially to our invited speaker for this great opportunity. I do believe all of us had really fruitful times here. Yeah, I received many great informations from your current work. So hopefully in the future also this kind of setting can inspire, yeah, all of us, especially the participants, to improve, to develop the research, yeah, especially for the one who really related, yeah, with the topics that delivered by our presenter today for the invited speaker. So finally, we come to the end of this session. Again, thank you so much to all invited speakers and also to all participants. See you again in the next seminar for our second seminar, as we informed before. Please stay safe, yeah, keep healthy, and don't worry to be happy because happy is the most, how to say, best strategy, yeah, to prevent the COVID-19. So everyone, see you again on the next seminar. Thank you so much.
Yeah.
Thank you.
Thank you very much.
Thank you.
Thank you very
Yeah.
much, Prof. Pakkorn, Dr. Witri. Yeah, Grandprix. See you again. See you again.
See
Yeah,
you.
thank you so much. Yeah, see you again.
bye-bye.
Thank you. Bye bye.
Assalamualaikum.
Bye bye. Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih banyak semua peserta. Thank you so much to all participants for your great participation, yeah, to stay with us until the end of this session. It's really great for us to have you. And again, I would like to welcome you back on our second seminar. Hopefully, this program, yeah, can give you the benefits and also the opportunity, how to say, to strengthen your research work, yeah, especially on the polymer, composite, and in general in the material science technology, yeah. So thank you so much again for your great attention, and we will share the materials of the presentations as well as the e-certificate to all of your email address that provided through the link that we informed before. Okay, stay healthy, stay safe, everyone. If you want to open your mic, we would like to welcome, even though just to say hello to other attendants. So yeah, see you again. See you again next time. And I do apologize for any kind of circumstance or even though the, how to say, in conveniency, yeah, during hosting this seminar. Again, thank you so much. You are so great. Yeah, thank you so much. Thank you. Yeah, thank you. Thank you. Music already. And if you would like to re-watch again this seminar, we provide the record on our YouTube channel. So please kindly visit our website. Yeah, you can visit our website address in Departemen Pendidikan Kimia. Yeah. Yeah, Departemen Pendidikan.
Thank you.